Well, thanks for having me. My name is Brennan Laidlaw. I'm a mechanical engineer. I've been working at Mickelson Coward, and I've been involved in building automation for, well, going on 20 years now. So I thought it'd be really fitting to just share some advancements in automation and how, and that advancements in technology can actually automate buildings. So with that, I just want to define what I'm talking about a little bit. So when we're dealing with higher level like automation or like using analytics to automate buildings, we need a prerequisite. We need a smart building system in there already to be analyzed. So that could be, today we're focusing entirely on mechanical systems. And that could be a lighting system, what have you, but today is on mechanical systems. So we're taking all that data that's being generated in an analytics system or like by the building automation system as an example, and we're moving it to a different data source for it to be analyzed. That could be in a cloud or some sort of server with some horsepower where you can use analytic rules to figure out what it's doing and self-diagnose the problems that you're having. And I've had the pleasure of working with data analytics and this type of technology and seeing them grow over the last 10 years. So I want to share some examples of use cases in optimizing buildings. And the second and third thing I want to talk about today is some really exciting technology for automated commissioning of buildings. And that's using like an automated tool that will actually command your equipment and it'll run it through an automated series of tests so that it'll automatically generate a report and try to self-commission them, so to speak. And then lastly is an automated system optimization, which is a fancy term for basically taking all that data that's in the cloud and actually doing something and starting to turn your building into like more of a self-driving building, so to speak, and it's optimizing it maybe by your set points or making adjustments for a net benefit of improvement. So that's the what, but maybe I'll the first example, and I really like this because it's a very simple example, but how do you measure comfort in a building? Now, comfort usually is by complaints in a building, like it's too hot, too cold, but never really quantifiable. So how do we use data analytics to quantify? This is an example of, say, an office, a school, any zone in a building, really. Let's take that temperature thermostat. So the green line is the set point, the red line is the actual. So what analytics will do is it'll analyze everything in your building. It'll define parameters, what's good and what's bad, and how long is it within that range. And it'll use its algorithms to figure that out. So in this simple example of being occupied from 6 a.m. to 6 p.m., 12 hours, this was only in an acceptable range, 9 of them. So I'm going to relatively score that as in 75%. 75% of the time, it's doing a good job. So let's extrapolate that. That was one room, one office in a building. Let's look at all of them. So this is a report run for 46 offices. And when it was analyzed, 42 of them, or 91%, are doing well. So just as a simple checks and balances and benchmark, analytics can be used to quantify actual, temperature performance and comfort in a building. And it can be used as a tool for optimization because you can track and trend that key performance indicator over time. And you can use that if it's going up or down or your optimization programs are doing what they want to do. So that also can be used in your optimization efforts because now you can list your best and worst performing areas and you could focus your attention and time, be it your maintenance or optimization, on worst performing systems as opposed to best performing systems. So again, example of using technology in a different way, in a very powerful way. Taking a little step back now, what does that mean for energy? So one of the techniques you can do is taking all that data from your building automation system, all that motor data, all that functional data, and apply calculations to it. So it's an example of a building automation system that ran all of the mechanical system in a building. And we looked at every single fan, motor, and horsepower, and we calculated all the motor loads based on that data, using energy calculations in combination with nameplate data. So we were able to give a totalized view of the amount of energy being used in the building, which was used as an ongoing commissioning tool just to see all the individual components. So this would be a total building view. which you can drive into like, hey, I want to see how much of my air handling units using for energy. Then here's all your different air handling units. And you can even drill down inside the air handling unit and say, oh, this specific fan is using this much energy. So it's a way for you to turn all of your like motors and basically all your equipment into energy meters without actually installing an energy meter, just using programming and proper calculations on energy. So very good use case. But now I want to go into like actual buildings. So this was an example of using data analytics as a retro commissioning tool. So they were applied. This was a building, a large office building in Manitoba, where we applied it in April of 2020, and data started flowing in. So immediately what we saw was we're looking at a steam heat exchanger, by the way, which converts steam to hot water. And we noticed right away that, okay, in the summertime, it's using energy. It's using a fair bit of energy. It's using a lot less energy than the wintertime, but why is it using so much energy? And the solution was it was actually running too much, and it was constantly running and generating heat in the rest of the building. So we put in an optimization program where we changed the sequence of operations. And the next year, running the same analytics, we saw a definite decrease in energy usage in the summer, and that amounted to about $10,000 a year in savings just on this measure alone, because it was such a large building. And you know what? Don't simultaneously heat and cool. Another example, and this is an example for a use case and the importance of ongoing commissioning. So this was a LEED Gold building in Manitoba. It was an education center that the project was done, everything was commissioned. We added analytics to the system a couple of years after the fact. Luckily, the owner had a long-term data archiving solution. So they kept all that data. All that data was there. So even though it was a couple of years after the fact, we were able to back analyze everything. And what we found was there was a lot of a difference of an energy usage for their mechanical systems, like in 2019 versus 2020. And a lot had to do with, not getting into the full details, but a lot had to do with how the building was being used. They were using the building in a different way to a higher capacity, which would cause the mechanical equipment to run a little bit more, which we used a lot less free cooling through the automation as a result. So that's a good example where buildings are being used differently, and it affected their energy like through a cascade effect down the line. The last sort of data analytics example I've got was just, this is an office building, and their performance was doing well, like 76%, very well. But what was happening was there's a lot of cooling issues. Like they had a lot of big areas like training rooms and boardrooms, and that was causing, because these had such big cooling loads, like it was causing the office area, that it was forcing it into cooling, causing the office area to overcool. So what we did, and not most energy efficient, but we allowed that reheat coils in the ductwork, the little heaters, to turn on in the summer. So yeah, a little bit of simultaneous heating cooling just to trim a degree or two. And we found that that was able to satisfy comfort at the addition of a little bit of cost. So this is an example of, remember, not optimizing buildings, not always about energy, but it can be about improving performance. So the owners now made an informed decision. They got a better performing building and comfort, but it cost them an additional $697 over the summer. So that's their decision to make. The next technology I want to talk about, and I'm shifting a little bit from data analytics to more of an active technology. And this is something I believe is going to progress a lot more over the next 10 years. It's automated commissioning. So these are just essentially a system that in some way can automate the process of testing equipment. So it'll command it to certain values, and it'll look at the response, and it'll try to see if it's getting the correct response or not. So this is something I see really beneficial for growth in terms of all the zones in a building, like all the terminal units, because even when we do a full commissioning of a building, usually it's a sample test, like, after it's been commissioned. Everybody doesn't go through like 100% tests. It might be a 10%, 20% test. So here's an example of commissioning VAV boxes, which they're little dampers that open and close to allow more heating or cooling airflow. So in this example, the automated commissioning system will pick a time of the day and it'll set a certain number of VAV boxes to 100%. and it'll look at, say, what the airflow is coming out of them. Then it'll set it to 0%. And then it's going to see, okay, is it actually fully closed? Then it's going to set it to intermediate levels and see, relatively speaking, is it getting the in-between values that we're expecting in the system? And you can do this on like fan coils, you can do this on any number of zones, but what it will do is it'll keep recordings of those values and compare them. So it's doing it at a higher level of analysis than you would get on your typical like automation system in a building, where you would need a technician to do it. And this is an example of a report that you could expect. So like in the first example, I got a VAV box, which is again, that heating or cooling air valve that's opening and closing. It was able to pass a low airflow test. It was able to pass a damper leakage test, but the damper response was different. So it noticed that 171 liters per second of airflow, how much air, at 50%, that's what they were getting, was actually more than the 167 you got at 100%. So that's telling me the dampers at 50%, you should get more airflow than at 100%. So something's wrong with that box. It needs to be checked. The next one was an example of a low damper leakage. They set it to 0%, but it's getting 44 liters per second of airflow. So something's not right. It's not mounted properly. The seals are broken. But it's a good example for the use of automated testing. And I really see this technology growing for ongoing commissioning and building maintenance, because like I mentioned, I've been working on automation for 20 years, but I can tell you there's no controls like a shop in Winnipeg, in Manitoba, that's testing the zones in their building ever. They just don't have time, or their maintenance tasking is not paying for it. Like, so having the ability to automate this test would be filling a void that's happening. Now, I don't see this replacing the commissioning process. I get that question a lot. Absolutely not. I'm a big fan of the commissioning process. That needs to happen. This could develop into a tool that could aid the commissioning process, because this tells you what's wrong. It points at what's wrong, but it doesn't provide that de facto root cause analysis, which you'd get a commissioning professional in to find. So definitely something to look at over the next couple of years. Third technology is, and this is kind of where it's getting exciting, and this is going to grow rapidly over the next 10 years. This is taking all that data, you're analyzing it, and actually writing back to the system, starting to adjust the set points on an automated basis. So you have like an AI operator, so to speak. That's kind of the vision of it, but an automated optimization system. So it's taking all that data, writing it back, and adjusting your set points or your parameters in the system. And the example I've got for you is, you got a fan, a big air handling unit in a building that has a VFD that's controlling the speed or like how much airflow is going through the building. And this is an example how an automated system can apply like known principles like ASHRAE's guideline 36, which is it's called trim and respond controls. It'll look at all the zones in the building, and it'll determine whether it needs more or less airflow. So it can bump the set points up and down. So the graph on the left was the before, using a standard sequence, which is just your single set point. The red line is your set point, and you can see the blue, the pressure that goes up and down at occupancy to maintain that one static pressure set point. And the one on the right is after it's been automated. So what it will do is it'll send 5-minute set points to the building. Every 5 minutes, you get a new value based on what every zone in the building's doing, how many requests, and it bumps the pressure up and down dynamically. So one simple example, but you're going to see a lot more of this grow. And you know what, hopefully a very standard methodology to it. So it's not, a black box, smoke and mirrors, etc. But this is something to keep an eye on over the next 10 years. And hopefully it's applied judiciously so you know what it's doing. So it's like, everybody's got the idea of a self-driving car and you don't really know how it does. But this at least gives you some validation and, hey, we know how it's doing, we know what it's doing and why it's doing it. So with that, I think I can turn it over to Matt, next speaker.
Great. Thanks very much, Brennan. I hope my audio is coming through here. I appreciate you shouting out that you're not trying to put me out of work just yet. It's very good. I don't know if I need you to, I think
Yeah,
I need you to stop sharing before I can share.
yeah. I'm sorry. There we go.
Oh,
There's the stop share button.
there we go. Uh, okay. Great. So I'm Matt Froese with Crozier Kilgore, and I'm a mechanical engineer. I work in building commissioning, technical leader in commissioning for Crozier Kilgore. So I work on a lot of buildings, and I have too many slides in my presentation, and I didn't take any of them out. So we're just going to move fast, and if you have questions, I can circle back to it at the end. I've got lots of time. Um, so we're just going to talk a little bit about kind of relevant standards for the commissioning process in terms of this ongoing optimization that we can do and how that fits into digital tools. Having the right plan for what to do when you're looking at optimization. Some areas where we see high impact optimizations and high impact issues, and then some critical commissioning questions to sort of guide how to think about this at maybe a higher level. I'm not going to talk about any of these standards in detail. I know this is being recorded. You can go back and take a look at the screen. There are a bunch of standards that apply, and there are a bunch of standards that are really thorough, and you can take a look at. I just want to kind of highlight this one piece here that I like a lot, which is from CSA Z320. So this is a commissioning standard for healthcare. But it talks about commissioning not as a one-time event, but commissioning is something that's required from time to time to maintain optimum performance and efficiency. So this can either be intermittent or continual. And I think what we are seeing, Brennan talked about some of the automation potential there, and I know Krista is going to talk about digital twins. What we're seeing is, I think broadly, that we have lots of equipment that's becoming much more sophisticated and complex, and there are lots of ways that things can perform very, very well, and also lots of ways that that performance can drift. And keeping an eye on that in the future is going to become increasingly difficult. So this ongoing commissioning process always assumes this kind of role of ongoing monitoring technology, but it can't ever just be a technology piece. You got to have the physical and financial resources to back it up. You've got to have an operator who's ready to respond and has the staffing and resourcing to say, hey, if this sequence says this VAV is broken, do I have somebody who can go look at it and fix it and get parts? All that practical stuff still kind of has to be there. In thinking about how to approach optimization, I think what I really want to communicate today is, do you have the right questions? Putting together a plan to say, are you worried about that kind of VAV damper level issue because you just installed a bunch of VAVs? Are you worried your VAVs are older and breaking down? But do you know what to monitor and when to take a closer look at what you've got? I think that's a big question, because we've gone from buildings that have very little data or no data in some cases. You just had that round thermostat on the wall that kind of turned everything on or turned everything off. And now we have some people who are so flooded with data that they don't have time to look at, that maybe they answer the most critical alarms and maybe they fix the equipment that's broken, but optimization is pretty hard to reach for. It's a lot that can get lost in the shuffle. And this is my fallback. This is Timothy Geithner quote from 2008, the financial crisis. He said, U.S. Treasury Secretary, said, plan beats no plan. If you're facing a critical overload, and I think today in a lot of buildings we have a data overload, there's just too much to look at, you need a plan. And any plan is better than having no plan at all and not looking. And I have to say, in my experience, there's a lot of people with a lot of data that they don't look at. So some areas of high impact optimization here. We're going to talk a little bit about outdoor air and ventilation management, a little bit about occupancy schedules, really basic fundamentals, some stuff about dampers and sensors, a little bit about heat recovery, and then heat pumps and refrigerant leakage. I'm going to move fast. So outdoor air is a big deal. We need enough ventilation to keep people healthy and safe, but it drives loads in a really big way, especially in our climate where we get really hot and really cold. So this is a local building that we're working on. And this is just an example. What you see there is kind of monthly energy usage on the blue bars, and the kind of orange or whatever burnt orange color there. That's the heating degree days for every month for the last 2 years. And what we found looking at their data is they had a 34% increase in total building energy use from the winter of 2024 to the winter of 2025. Heating degree days shifted a little bit. We had a slightly colder winter last winter, but it moved by about 7%. So there's a big shift there. And it came down, as it turned out, to a single override for one piece of equipment. Their central ERV for this very large building was put to 24/7 operation for the entire winter. And it meant even though they had a sophisticated building automation system, they had a schedule for the equipment that was appropriate and did work for many years, somebody left an override in place for the entire winter, used about an extra 250,000 kilowatt hours. So that's probably, including demand charge increases, something like a $30,000 touch. So that's an expensive choice that somebody made that nobody knew about, and actually was undone by the time we got called in to look at something somewhat unrelated, and this kind of popped up in our review of their data. So this is one of these cases where I am very hopeful that stuff like digital twins and ongoing monitoring could let people know, hey, you're a month in and something's off track, because 6 months in, those bills are due and there's nothing you can do about it to get that money back. Hydro wants their cash, they're going to get it. So outdoor air, we also see a lot of drift, I think. Standard recommendation is periodic rebalancing, which I'm quite sure almost nobody does. We see a lot of damper leakage and kind of breakdown in equipment over time. So this is just a quick example of a case where we had an existing building with parallel redundant air handlers and no local control. Nope, not even any original performance records. But what we were able to do with just some local data logging is take a look at supply temperatures between two systems that we knew were having some problems. So these should be identical, but our supplier on the one side there is hitting our performance range sort of when it's being called on. You can see on the left side, we're getting into that 12 to 14 degree supply range for cooling. But air handler 2 on the right, basically never getting there unless it's overnight and it happens to be off and it's just cold outside. That's what that temperature sensor is saying. So that data just lets you know something's off, but doesn't really tell you what until we add just a third data point, which is the outdoor air temperature at the time. And this is a fun chart because this is a negative space chart. What's important here is kind of the performance envelope. So as the outdoor air gets warmer, as we're going up on the left axis there, air handler 1 is still able to push pretty cold air, but air handler 2 never manages to push cold supply air. No matter what it's doing, no matter how hard it's running or how long it's called on for, we can set aside everything about control cycling, everything about response times. It just never gets there. If it's 24 degrees outside, it's pushing supply air over 16. It's not doing what it ought to do. And we could find that with 3 data points. Now, in this case, we had to kind of go panning for gold. We had to go physically place a sensor. We had to collect the data, had to analyze it by hand. But this is the kind of thing that could absolutely be automated to say, hey, you've got a fundamental performance issue. And even though somebody told me that they had checked the damper, they actually hadn't. We went and found that damper was just leaking a substantial amount. And after correction, we managed to get the 2 units for 30-year-old units performing nearly identically with a simple mechanical fix. This is another building we looked at, just had a controls upgrade, new damper actuators. Is your closed damper closed? And is your automation system giving you real information about what's happening mechanically? You can see the daylight through the damper, it's probably not really getting closed. And the same system, at the same time, they had new CO2 sensors put in for demand control ventilation. Neither of them had been calibrated, and they were both over 100 parts per million off. So our offset was larger than, in this case, the signal we were looking for. So with any of these systems, garbage in, garbage out is still going to be a problem. You need people who have time to go validate and to check and to notice, wow, that number doesn't really make sense. It's not moving in the way we expect it to. And then what do you do about it? This I'm going to blast through way too fast. Hidden costs of heat recovery. We're building a lot of systems now that are a little bit complex, and we're trying to use heat pumps for heat recovery in a lot of buildings. And I think one of the questions that comes up is, do we have the data real time to know if we're making good operating choices? And a lot of the times our sequences are sort of preset. They're fixed to say, in this condition, we're going to run this equipment. It's going to control to this set point. And we maybe do some of that trim and respond set point adjustment, but those big choices are sort of fixed ahead of time. And one of these places I think that can fall apart is when we're recovering heat from big chillers. So I've got an example here. This is a real piece of equipment that we're working with. Big 200-ton chiller running one of the new refrigerants, R513A, 200-ton unit. Pretty big. Don't worry about the numbers. But the important thing is, so just in terms of its loading, at full load, it's going to use 168 amps to run that compressor. But at 50% load, which is more where the building's going to run most of the time for most of the systems we ever see, if we can run our condenser loop cooler, if we can reject heat at a cooler temperature, because that's why our load is lower, it's a day that's not super hot outside, our load on that compressor falls substantially. So we see savings beyond just a linear relationship to the load. The unit gets more efficient. But if we have to run the condenser side hot so we can recover that heat usefully mechanically elsewhere in the building, our compressor load goes up. And we go from, in this case, for this real piece of equipment, 76 amps up to 110 amps, 600 volts. So it's a lot of power. And it's a 45% increase in our compressor power demand. So at some point, there's a real question there about, do you know that you're making a good decision about using that much electricity to run your compressor harder? And what could you do instead if you have options to, say, run reheat more efficiently if your reheat demand is very, very low elsewhere in the building? If you can't use it efficiently, does it make sense to do this at all? Yeah, and then getting into the last bit here, just on heat pumps. This is a real unit. We worked with a geothermal heat pump that had been in operation for a while. We got there and noticed there was something going on. Both compressors in this unit here at the end were running. They started when called, and there weren't any alarms, but when one of the compressors ran or said it was running, there was no change in temperature in the system at all. Nothing seemed to happen. So we went out to take a look at it in person. You got to go see what's going on in the real world. And this is an infrared shot of those two compressors, the same things. The only thing you need to know about them is when they're working, the bottom is cold and the top is hot. That's what the compressor is doing. It's moving heat, and the brighter colors there are hotter. So what we found here is the difference between that first compressor and the second compressor is that when they were both running, they would draw the same number of amps because they're both running, but the compressor on the right was the only one actually doing any work. The leaving refrigerant temperature was 20 degrees Celsius higher, and it was the only part of the unit that was really working. So they were both running up the hydrometer for the owner, and they were both doing exactly what the system asked. Nothing was reported as alarming or broken. There was no direct data to suggest anything was off track, but the one on the left wasn't working. And I found, so this is a study that came out just earlier this year. This is a bit of a chart on impacts of leakage, refrigerant leakage on system efficiency. And this also goes to capacity, but this is the efficiency graph. So a lot of our current heat pumps use mixed refrigerants. So R410A is a blend, R454B is a blend. This particular study uses a non-commercially available blend, but it's the same component parts. So I think it's comparable. And what they're looking at here is as you lose more and more refrigerant, your system efficiency drops, and it falls off pretty fast, starting at about 20% loss. And not only that, because we put these heat pumps in different operating conditions, leaks at different operating conditions and at different times of year, especially if you're looking at air source heat pumps, are actually going to leak different component parts. So the refrigerant doesn't leak as an even mixture. As it's leaking, the refrigerant composition changes and the refrigerant performance changes. So that's why the kind of light blue dots there get more and more spread as you get further apart, because depending on when it's leaking, what you're working with inside the machine is physically changing, and the output from that machine changes. So most of the time, if what we get at the control layer is, did we ask it to turn on? Is it running? And are we getting any alarms? You might not see that you've lost 40% of your refrigerant and maybe 50% of your efficiency. And if you're in Manitoba, where 50% of your efficiency might mean the difference between making sense to run a heat pump versus just running a baseboard heater, that's a big deal. And missing that, I think, is a big deal. Right now, I've been looking for some data on net refrigerant losses in the province, and that is apparently not public data. But I'm told my Freedom of Information request is going to turn up some data very soon. So maybe next time I'll have something on that for you. So just getting back to these kind of high-level questions, I'll wrap up and hand off to Krista here. I really love to see more information and less just sort of data in our industry. I'd love to see more feedback for owners about how do we know when our system is drifting? How do we know if we're getting what we paid for? Do we have a good baseline? Are we looking at it often enough? Do we know if we're still able to hit our peak loads? Do we know that we're hitting our part loads efficiently? And then, yeah, are we meeting our emergency conditions, or do we have that tight temperature control that Brennan was also talking about? And I think those are questions that can really guide the way we think about what these tools are for and what they can do for us. And that's what I got. I'll hand it off to Krista. Thanks very much.
Thanks, Matt. I'll share my screen. Everybody see that?
Yep.
Excellent. So my name is Krista Wright, and my role at Bird is I run a national engineering team at Bird. So my background is electrical engineering design. I was a consultant for about 15 years and came over to the construction industry and built a team of designers and system specialists that work with all of our industrial buildings and buildings groups across Canada to support from an engineering standpoint. Often I'm in the room with the owners at the front end of a project, trying to figure out what our scopes are, how we mix with our consultant partners, and what the project goals are. And often I'll say, okay, we need to start at the end and go, what are we trying to accomplish in this project? And I don't mean at the end of handover at construction, long life. Let's think about the end goal, and let's bring that back and see how we can work that in to our process of design and construction and commissioning. And that brings us to the conversation of digital twin. Digital twin comes up a lot in terms of a conversation. And so I'll just I'm a lot like Matt. I have too many slides, and I will breeze through some definitions just so we can level set what we're talking about. And I'm going to walk through a case study just to share some of my experiences around digital twin and how we're trying to loop all of this information together in automation. Yes, there we go. So I work a lot with our digital construction team at Bird, and some of these slides, the ones with a lot of words, are Tanner's, not mine. I talk more rather than type, but some of these definitions he's pulled in the digital construction side, and they might even be, some people may not agree. But IBM defines a digital twin as a virtual representation of an object or system designed to reflect a physical object accurately, spans the life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to make decisions. And basically, Tanner's interpretation as a digital twin is the product of building the connection between real-time data points from initial conception through to decommissioning and recycling of components. So we're basically looking at the entire life of the asset and using real-life data, much has already been discussed, to do that. A lot of the information that would be in a digital twin is listed here. The big thing is we're connecting what I call flat data, live data, sticking it together, and using the information that's coming from real, actual operation to inform future decisions and automation and moving things forward. So there's a whole bunch of things that it's right from design right through to facility operation. In a construction application, that's usually where Bird comes from, is like we like to use versions of a digital twin for all of these components and reasons. Biggest thing would be risk mitigation. We use a lot of the tools that Matt and Brennan both touched on in terms of technology, so that we can improve our commissioning processes and hand over more efficient buildings. But basically, the digital twin helps us to better plan and provides data to back the decisions as we develop it. This is a grocery list of how automation and machine learning, what the advantages are, what are the applications. I think there's about 20, basically just showing you the real life case for, this is a good thing, and we often push it to our clients as consultants and builders because of these reasons. But unfortunately, there just aren't enough versions out there for people to see, believe in, and see the actual practicality. But it's all about efficiency. So machine learning, AI, and automation often get confused. We consider machine learning is taking information as things are going through an analytics and feeding it right back into how the algorithms are defined and updated. So basically, if we're performing a function and then there's this output, we take that output and feed it right back into that algorithm to refine the algorithm, and that the machine is actually improving itself based on real data. Automation is often confused with AI, and it's designed basically to streamline tasks and workflows. And automation is often best applied when we're talking about routine tasks that are timely, lots of room for error, or just things that, similar to the things that Matthew pointed out, where you don't just see, but an actual tool, digital tool, can pick up and give to you. Larry Page, who's a co-founder of Google, says that artificial intelligence would be the ultimate version of Google, the ultimate search engine that would understand everything on the web, would understand exactly what you wanted, and it would give you the right thing. We're nowhere near that now. However, we get incrementally closer to that, and is basically what we work on. So AI is just taking inputs from all over the place, all the different components, all the different parameters, all the different factors, not just mechanical, electrical systems, not just sustainability, data, energy, GHGs, but everything around it and all the possible things that could be impacting it. But I really love this quote on the bottom, and this kind of leads into the case study. Technological progress has merely provided us a more efficient means for going backwards. And, I actually, I love it, and I have my own thoughts, but I put it into ChatGPT, disclaimer, to see what ChatGPT said about that. And basically, there are 4 key points. Efficiency does not always mean progress. Just because we're doing it faster, cheaper, more powerfully doesn't mean that we're improving the quality or we're improving human life. Tools amplify direction, whether they're good or bad. There's often a loss of wisdom or humanity when we use machines to automate and think for us. And when we rely too much on technology, there's often progress without purpose. And I think that's a lot of why some of these proposals for digital twins, we get very excited about the technology and what could be and what we can do. But if we don't have smart people like Matthew, like Brennan behind this, that understand those systems and understand the why, what are we looking at? Are we really progressing? And these things can get expensive and cumbersome, and basically that's a path for people to just pitch it and abandon it. So what I like to do when I approach these projects is no, we don't want to abandon digital twins because they're expensive and cumbersome and too much for our teams. We want to start building the building blocks so that we can learn how to basically use technology to improve what we're already doing, and then learn more about how we can do it better, and set up our projects so that openness is there to keep expanding on it and learning and everything. And the first thing you need to do in this, I always say to the clients, is what are your goals of this project from a sustainability standpoint, from an operations standpoint, a technology standpoint, marketing? What is it we're trying to achieve, and how can we use technology to wrap that in? So, there isn't one defined definition of digital twin. This is what it is. I mean, we provide definitions and views, but we kind of use this framework as how we can build the blocks to set us up to build something and digitize an actual asset and put in the meaningful information that's going to help us with efficiency, with planning, with budgets, with operation, and maybe learning and teaching and, providing a living lab. But then we don't know today what we don't know. So as we get more information, kind of like machine learning, we can feed that in and we can add. Most of our projects are already modeling our assets in 3D. But then if we collect historical data, this is all about data. it's all about collecting data and what data is meaningful. Whether it's coming from historics on operation, whether it's coming from sensors that we connect, temperature, humidity, how many people are in the room, things like that, as well as weather and status of like a door being open or people using a space. And basically, the more data that we can put into a system, the higher probability that we can incorporate machine learning and then AI into a digital twin that actually operates itself, which is it. So we as Bird had put together, we're currently building the Student Center Redevelopment project at SAIT in Calgary. And, this is one building on a campus of many buildings. And there are a number of companies that are already on the site utilizing existing programs. And we talked about, and BGIS is managing the facility. So we talked about initially at the design phase, do we want to implement a digital twin? And what does that mean? And how can we do this most cost effectively? So we did have some kind of discovery sessions with the owner. And when I took it back to figure out how, the what and the how, these were the guiding principles that we use. Number one, is it practical? Does it actually improve facility management processes? Because that was the big target. They were already utilizing Coppertree on site to optimize their building systems and monitor their energy and GHGs. And does it make economical sense? That is always the question. How much does it cost and how much am I going to save? Everybody wants to know that. Does it reduce complexity? Can we consolidate the information from various sources into a single pane of glass with practical information, insights, and processes? Will users need special training? How can we reduce the complexity of the program so it doesn't become a roadblock for implementation with the facility management team? And then minimal capital and operational costs. So this is not the primary driver of the project. And the project, as you know, everything always escalates as you go through. So how can we do this at a most cost-effective way? These are the components that we wanted to put into the digital twin to start. Design, construction model information, O&Ms, costing data, live monitoring, analytics, alerts, notifications, and then operations and maintenance history. And basically, I looked at what we already had in the base contract from the components that we would need to build a digital twin and what would be considered the additional scope to what was already there. And the additional scope is basically creating an FM model, a facility management model, and that fed into a digital twin that would ultimately use machine learning and AI to manage the facility. Like I mentioned, Coppertree was already on site. Their buildings doing a lot of the doing all the monitoring and analytics for their building systems, and they were using Archibus as their program to manage the facility, manage the assets. And this was a program they already had in place that the team was used to using. So what I did was I went, okay, so we've got Archibus, we've got Coppertree, we've got a 3D model, we're going to have a construction model. How can we marry this all together and utilizing processes that people were already used to at a very low cost? So I reached out to Archibus and I said, yeah, we have a digital twin module we can add on to this facility management program they've already got a license to. Minimal cost to add the module. I called Coppertree, they're like, yeah, we can write some code that'll integrate our live energy data into Archibus. And yeah, we can feed our 3D model into Archibus so that they actually get that visual in the program along with all the asset and O&M data. And there's a bunch of middleware and details, but yeah, we can do this and pull it together. So it's not a huge leap for the team. So we brought in Archibus to do a demo of the digital twin. And then we basically looked at all of the groups that were involved in the project and broke down all of the different components of building this digital twin and who would own what. Then we looked at what the additional scope would be. I removed the costs because I knew this to be recorded. So we're not providing the cost of the project, but each one of us groups kind of put a cost to it, a high level cost, went to SAIT and said, is this something you want us to look into and explore further, develop? So that is that's the gist of my case study. Sorry, squirrel. But basically, I think what's important to realize is if we are trying to improve efficiency and if we're trying to push technology in a way that actually makes our projects better and more efficient, we can't go to the owner with those big, sexy, sophisticated pictures I showed at the beginning of this presentation, because it's just far too ominous. They're seeing dollar signs everywhere. They're not seeing practicality. What we have to do is break it down into simple building blocks that make sense for them, and it's practical. But then there's certain principles that we can deploy during design, procurement, shop drawing reviews to make sure we're set up. Like, if we're going to have all of these programs, they have to have an open communication protocol. So nothing proprietary. Everything has to be able to talk. We need to collect data. We need live data. What data is going to be meaningful? What data is going to help us in consistently improving the performance and efficiency, or the operation procedures, or capital planning, or, in a lot of cases, we have a lot of post-secondary clients. They're like, we need to show this big, sexy 3D model that's loaded with data, because we've got all of these students coming in that actually, when they were 2, they had an iPad and knew how to use it. They're at a different place than we were growing up technology, and they want to see that we're advancing and they can build on it too. So really important to know your audience and know your clients. But I don't think that this is an impossible thing to sell and implement. And I do actually think that it does bring value to projects. And that's it for me.
Oh, thank you so much. Really appreciate all of this. I'm just going to add us all back on here for the question period. So folks, you can send your questions in the chat, or you can also raise your hand and we'll ask you to share your question. So the first question is, as tech becomes less expensive, do you envision real-time IR/UV cameras being used to monitor equipment and integrating into BAS decision systems? Who wants to take that one? Maybe all of you. I don't know.
I'm not sure if that's a question for me, because I did have IR photos in my presentation. I think so there are industries that do have infrared monitoring, usually like high capacity, high test electrical installations might have some ongoing IR monitoring if they're looking for hotspots in switchgear, that kind of thing. But I don't know. Beyond that, I think you'd need some pretty reliable machine learning, where most of the time, like, we can put temperature sensors on things and it's pretty straightforward to do. So I think there'd be a question about what that additional complexity is getting you as an advantage. I know there was a research project through ASHRAE, I want to say 4 or 6 years ago, where they were using like infrared mapping to try to map like how thermal comfort and surface temperatures varied across occupied spaces. I think there's a lot of potential there in the future. It's like people need to make that commercial. But if we could figure out how to scan a space in real time and say, oh, that corner is hot and that corner is cold, and now we're going to do something about it, there are a lot of uncomfortable people in a lot of spaces who would appreciate that.
I do have a real world example of that. I've seen ceiling mounted sensors that are really available. And what they can do is they can scan the room at a very low level cost. And they're looking for heat blobs in the room. So it's scanning the room to get an average temperature, and it's looking for little heat blobs to count the amount of people in the room. So that's not, maybe in your example, asking to see like maybe what Matt showed about the compressors being too hot, but it's being using IR in a way that's, outside of the norm. It's for temperature control and comfort of the room, but it's also using it more intelligently now to count people. So it is a now technology, but depends on the application again.
We're getting some positive reactions through the old emoji use, which is nice. It's kind of fun. Are there any more questions? Anybody want to raise their hand? Oh, wait, we have a similar question for Brennan. If you have a similar case study for individual residential homes.
Individual residential homes? The answer is honestly no. And part of the reason is everything I do at my company is commercial. So I would be the wrong person to ask for that because that's just outside of my everyday job for the last forever.
Have you heard of anybody who's doing this at the residential level? Anyone?
I mean, I
Yeah.
think the thing that's out there residentially is, a bunch of stuff from folks like Google Nest or whatever, where you can, although the asterisk probably don't do that, but you can get more distributed temperature sensors across your house, so you can get room by room temperature sensing residentially. I haven't heard about anybody doing IR temperature sensing residentially, but zone by zone, like room by room, you can get now for sure.
All right, coming up. How would the twin model be connected to categories D5 and D6? And I believe that's with regards to BMI. Would it serve only for KPI monitoring, or could it also operate hardware, functioning not just as an interactive model, but also as a real control system?
Again, I think you could use a D5 or a D6 model because it's all about inputting data and running analytics and AI and machine learning based on the data that you're coming in. So, I mean, I could see we haven't done it, but I could see how you could take, that the inputs from a D5 and a D6 and incorporate it into a fully automated operating digital twin that's running on AI. That'll probably come in the future. I haven't seen it today. There's components of it that you can run today, different programs, middleware that can take pieces of that. I don't think that we're at a place yet, though, where people are comfortable just leaving it to the machine to take all those inputs of those models to run the building. In fact, often, when I talked about, we used to develop SkySpark, which was middleware for optimizing building systems. And the controls contractors on the mechanical equipment did not only wanted us to use that middleware for monitoring, not controls. So we could take the input in, we could take all the data in and provide reports and analytics, but they did not want the program pushing commands back out based on those analytics because they just didn't feel like we were there yet. So it's an interesting question. Definitely can, but I think there's a lot of barriers to whether we will.
Fair.
Today.
Yeah. Okay, so there's just a question about what tool was used to create the digital twin.
Okay, so the tool that was mentioned, there's so many. And I think I'm trying to remember the tool that Bird typically uses. But in this case, it was a module as a part of Archibus, which is an asset management program that is already licensed at SAIT.
Oh, you're muted.
Goodness gracious. Classic mistake. Unmuted. Or muted, as the case was. In a universe of complexity, is there a motivation to avoid the Challenger effect in design and control an O-ring failure cause disaster? Where an O-ring failure causes disaster. Wow. Muting. Talking. It's hard.
Yeah, I mean, I would say yes, and I say that from my perspective of, so the retro commissioning work that we do here is often driven by people who are having serious problems, and I think if you dig into that, there are a lot of examples of systems today where people are trying to apply more complex technology, more complex building systems technology in ways that just don't end up integrating well or become increasingly fragile. A lot of old systems, electric baseboard with a line voltage stat is very reliable, and if it does break, there are parts at your local hardware store. And if you are, especially in Manitoba, like Winnipeg is a different thing, but if you get outside of the perimeter and you need to wait for to book a service tech to come out, and it's a 3-hour drive to your location, and there are no parts available in your community, like a 5-minute fix can really take days. And just for practical reasons, right? Can you get a part delivered? Can you get somebody who knows what it looks like to install it? Can you get them to the site? And I think that's the stuff where people who run buildings and worry about answering those questions about why is my office uncomfortable? Why don't I have hot water in my shower? Why can't I run a surgery in this operating room? Those are very real questions that people don't want incomplete answers to, because they need to deliver, right? Our buildings are here to serve people, to serve our communities, and when they don't do that, people get upset, and they probably should be. So we need stuff that works well all the time.
So as a final question, indoor air quality monitoring automation is becoming more important as residential scale, at residential scale in the USA, especially after forest fire, pollutant, health emergencies. Maybe that was more of a statement.
I think it's true. I don't disagree. There's also, Brennan is the president of our local ASHRAE chapter here in Manitoba, and ASHRAE has a standard out now, I don't remember the number of it, on managing wildfire smoke in HVAC systems, which is great if you're looking at more commercial scale.
Standard 44. Now, that's a worldwide problem, and Matt has attended some events on that, and I've learned a lot from over the years. But speaking for, let's say, example of healthcare, what healthcare facility managers are starting to do in Manitoba is start to figure out, what do we do when we have a wildfire smoke event? Because often the mechanical systems aren't designed to not bring in outdoor air. We've taken that as granted. Now we're talking residentially here. What can you do? And the answer is you're supposed to shut down your air damper. So what we're hoping on, it's not going to be a long-term thing, but they're starting to get processes in for like short-term, medium-term, and long-term smoke events, and what to do in those cases. And they're never ideal. So the answer is, the world's planning for it, the world's developing solutions for it, but we don't have a silver bullet that's going to answer everything. So we got short-term solutions, but not long-term solutions, and that's where design coming in. And that's where engineering is going to have to pick up the slack.
Mm-hmm. Yeah, and I think we saw this year. I mean, in Manitoba, certainly this was an exceptional year for wildfires. This summer was not super fun, and hopefully not a harbinger of what our new normal is. Because it's really challenging. It's we live in a challenging climate at the best of times. We want to take advantage of those outside times in the summer, but it's we have a lot of risks there. And I know beyond the residential scale too, there are a lot of, I'm going to say, like large crown corps in the province that are running increasingly large distributions at various levels of indoor air quality monitoring in their buildings, because I think people want to know, and as the cost is coming down, it's getting easier to know, do I have a radon problem? Do I have a ventilation problem? Do I have carbon monoxide problems? I picked up in my house, because I'm a big nerd and I have my sensors for fun, I picked up that I had a backdrafting condition from my hot water heater. And it's just, there was this weird spike in carbon dioxide in the house when it was just me and Lisa and the cat, and all of a sudden our CO2 was up over 1,000 parts per million. Went down to the hot water tank, and that exhaust was coming right into the house. So making that data available in ways that people can act on, including at home, I think is there's a lot of potential there if people know what they're looking at.
Yes, if people know what they're looking at. Good caveat. Well, thanks everybody so much for your time and attention. Special shout out to all of our speakers. Wow, that was so informative. I can't believe that we managed to accumulate such a great group of people to share so much good information. So thank you so much for your time. And we'll see everybody next time. Take care. Have a good day.
Great. Thanks for hosting, Laura. Appreciate it.
Absolutely.
Bye.
Bye.